Okay, first we want to talk about end behavior, perhaps of polynomials, okay? So I have 3 zeros here. Now, when I first drew this, of course, curve wasn't there, but we got a 0 here, got a y-intercept here, a 0 here, and a 0 here, and I've got to draw a polynomial graph, a smooth curve that goes through all those points. Well, I started out by drawing this one. And then I realized I was stuck, okay, because I can't go through this 0 and get to this one, or get to the y-intercept, because I don't have any way to go back up through the x-axis. I can only go through the x-axis at the zeros. So I'm stuck, so I kind of cross that out, and let's just kind of do this. That's a bad attempt, that doesn't work. Okay? If I'm going to start up here, of course there's no reason I have to start up here. I could have started down here and gone through this 0 just fine, right? So I could have drawn a graph that does something like this, but I decided I wanted to start here. The only way I can start high on this end and go through, or at least touch the 0 here, and go through the y-intercept here, is to turn around when I hit this 0, much like a parabola. Okay? So I turn around, then I can continue the graph. Okay? So example now of the end behavior, because I've kind of assumed that the thing just goes off and gets a lot higher here, goes off and gets a lot higher here. The way we explain that, well, let's just take an example. P of x is this polynomial. Okay? Now, make the statement that at points far to the right of x equals 5 being the rightmost 0 of this polynomial, for points far to the right of x equals 5, what do we have? For example, if x is 1,000, well, x minus 1, x plus 4, and x minus 5 are not going to differ significantly from 1,000. They're all going to be about the same size. They're all going to be about 1,000. So what I've got is I've got 1, 2, and 3, and 4 factors, all about 1,000. If I do 1,000 times 1,000 times 1,000 times 1,000, I get a trillion. So that means, well, we'll make this statement. Far to the right of x equals 5, all these factors are positive, and all are large. Okay, so large, positive factors, because if x is a large number, all these are going to be large. And if they're all positive, that means P of x is a product of 4 large positive numbers. Okay? And that's going to result in a humongous positive number. So if I go out to the right some large number, and then I go up some absolutely humongous number, what direction am I going to end up? Well, people kind of pointed, well, you're going to end up pretty high there. So for that reason, the graph just takes off like this, and I have a little arrow here indicating that it's going to do this sort of thing. It's going to end up getting steeper and steeper, but not approaching anything as an asymptote. Okay? And then far to the left of x equals -4 would be the leftmost of the zeros of this polynomial. You can make a similar argument. All 4 factors will be very large, but they'll all be very large negative numbers. So you're going to get the product of 4 large negative numbers. You get another humongous positive number. 4 negatives make a positive, so you're going to end up going up like this. So this might not be a bad representation of the behavior of the graph of this function here. Okay, at x equals -4, this is squared. That's going to give you this behavior at the 0. And these are just linear factors, so you're going to go straight through the 0 and straight through the 0. Okay. Well, that's one thing. Okay, now, gave you the function f of x equals 5 times 2 to the x. Ask people to get f of a, f of b, and so forth. People have more trouble with this than I expected, because we talked about this a little bit earlier in the semester, so we want to make sure we get this. So f of a is what we get when we replace x by a. So we replace x by a, and we get just 5 times 2 to the a. And of course, f of b similarly will equal 5 times 2 to the b. Now, f of x plus h. I remember writing this down wrong once or twice, but I kind of checked myself, got over that pretty quickly. So if you wrote it down wrong, you don't have to feel badly. But f of x plus h, you're replacing x by x plus h. Well, here's x, and x gets replaced by x plus h. Now, a lot of people wrote down 5 times 2 to the x plus h. Well, x hasn't been replaced by x plus h. X is still there as the exponent of 2, and then the h got slapped onto the end of that expression. That's not right. That's not what happens. This is what happens. So you want to be careful about that. Okay, well, after we got that, people were pretty good with the rest of it. F of x plus h minus f of x. Well, f of x plus h is 5 times 2 to the x plus h, and f of x is just given here. It's 5 times 2 to the x, so there it is. Okay? And then finally, f of x plus h minus f of x over h. Now this is important. We're going to see why in just a minute. F of x plus h minus f of x over h. Well, here's your f of x plus h minus f of x. But if you just have this expression facing you, you'd say, okay, f of x plus h. I replace x by x plus h, and I get this. And minus f of x, well, there's f of x, so we have minus f of x there. And then divided by h is just plain old divided by h. Now this thing's an important quantity. It's called the difference quotient, and it ties in with a lot of things we've been thinking about. It's maybe one of the 3 or 4 most important expressions in mathematics. Okay, now, the reason the difference quotient is so important, here we've got a graph of f of x equals 2 to the x, the function we were just looking at. So let's just say here's x, and here's x plus h. Okay, now, we ask, how do you locate f of x? Well, a lot of people drew a dotted line up to here, and a lot of people drew a dotted line up to here and then over to here, and said f of x was this value here. And that's absolutely correct. That's a good answer. If you just drew the dotted line, yeah, you were on the right track. But we want to draw this as an arrow, as we've done in trying to understand transformations. Okay, so we want to draw that as an arrow. Okay, so the length of this arrow is the value of f of x. And then here's x plus h. Well, the arrow coming from here up to the graph is the value of f of x plus h. Okay? Yeah, those should be clear, and of course you go back to the full video. Okay, so we want to show that we want to show f of x, and well, the task was show f of x and x plus h, f of x plus h, which we've done here. Now, down here, we draw a little bigger picture of this so we can label it a little better. So here's the arrow for f of x. We label that f of x, understanding that this displacement is your value of f of x, and this displacement your value of f of x plus h. Well, there's a fundamental triangle corresponding to the interval from x to x plus h, because of course, here's x, here's x plus h. I'm just redrawing this picture here, okay? And we can see that the rise of this triangle is the change in y, i.e. the change in the value of f of x. Why? Well, we know that that's what the rise means between 2 points. We talk about that a lot. And the run is the change in x. So this fundamental triangle has a rise that's equal to the change in the value of f, the change in y. The run is your change in x. Of course, the run, your change in x, is just what? It's h. From x to x plus h, that's h. Okay? So the slope of this triangle is the change in y divided by the change in x, which is the rate of change of y with respect to x. And think we ran out of time, I didn't get to say it. The change in y is f of x plus h minus f of x. The change in x is h, so that is our expression. F of x plus h minus f of x. Clearly from this picture, you subtract this from this, you get the change in x, the rise, and, I'm sorry, the change in y, and that's the rise. And here you have the change in the value of x, which is h. So there's our expression that we wrote down previously. Okay, a very important expression.